Hello and welcome to another session of the Digital WE Days. My name is Son and I will moderate this webinar today. The topic of today is practical tactics for designing SEPICs. Our speaker today is Mohamed Al-Alami. He works as a senior field application engineer at Red Electronic ISOs. SEPICs converters offer flexibility in power supply design. But how do you optimize components and deal with parasitics? Let's explore practical design strategies. Stage is yours, Mohamed.
Hello, thank you for joining this session on practical tactics for designing SEPICs. My name is Mohamed Al-Alami. I'm a field applications engineer with Worth Electronics. I come from a power supply design and development background. For this session, we start off by providing a general overview of the SEPIC topology. We will proceed to look at the more practical aspect of the design of a SEPIC converter. We'll cover things like continuous conduction mode, boundary conduction mode. We will look at the use of a single coupled inductor versus two single inductors. We will also look at things like ripple steering and the leakage effect. So let's start off with the SEPIC topology overview. So SEPIC stands for single-ended primary inductance converter. It's a topology that's more like a buck boost, so it steps up and steps down, with the advantage of the output being the same polarity as the input. If you look at the input stage of this topology, you see it very much looks like a boost topology. The output side looks more like a buck boost. And we have got this key component, which is the AC coupling capacitor, coupling energy from the input stage to the output stage. Another advantage of this topology is that this AC coupling capacitor blocks the DC current, so it provides an inherent short circuit protection on the output. One key design aspect of CAC is that it needs to have very low impedance at the switching frequency to optimize that energy transfer. Apart from this, you'll see that we have got two single inductors in here. You could also have one coupled inductor, and the remaining parts of the topology is the main transistor switch, and on the output side you can either have a transistor switch or a diode. Before I move on to the next slide, I'd just like to mention app note 135 is a key app note that was written by one of my colleagues, Eliatar, who has done a great job in trying to look at calculations, simulations using LT-SPICE, as well as doing some measurements. Most of the work in this presentation is based on this application note. So summarizing very briefly the basic operation of the SEPIC converter under continuous conduction mode, we'll start off with that. So when the transistor is turned on, we can see that the voltages across both inductors, in this case we're using two single inductors, but it could be a coupled as well, might as well. And in this case, you've got the input voltage impressed across those two inductors, and they are energizing, so energy stored in that inductor. And the ripple in that inductor is V in dt over L. And during that time as well, the voltage across this capacitor, the AC capacitor, the coupling capacitor, is the same as the input voltage. The output stage is isolated because the diode here or the transistor are switched off or reverse biased. So all the energy is delivered to the load via the output capacitor. Now, during the off time of the switch, it's open circuit, as you can see here. It's the diode on the output side that is conducting, transferring energy now from our inductor to the output capacitor, charging that up and delivering power to the load. During that stage, both inductors will have the output voltage impressed across them, and they will be de-energizing, as you can see here. Note that the average current in the input inductor is the input current, and in the output inductor is the output load current. I've included various different design equations associated with the continuous conduction mode, SEPIC, with single inductors. So there's a voltage conversion ratio. This is the ideal equation. We've got the calculation of both inductors, current and inductances, sorry, as well as the currents, of course, and the voltage stress across the switching devices. We've also got the calculation here for C in, C out, and CAC. Please do refer back to this application note. It has got quite a lot of equations and calculations with more accuracy. As you can see here on this curve, we've got the voltage conversion ratio versus duty cycle, and this is the ideal one. So in the application note, you will see also another equation that looks at parasitics, things like the resistance of the windings, the on-state resistance of the MOSFET, the drop across the diode, which will naturally reduce your voltage conversion ratio as you go up in duty cycle. So it limit that VCR. So in this section, the practical side of things, we will jump more into the practical side of designing SEPICs and look at various different aspects that you need to consider when you're designing this particular type topology. And we'll start off from where we stopped with continuous conduction mode still with 2 inductors. And this is based on an actual prototype board that my colleague had built, and he'd done the calculations for, of course, as we have seen on the previous slide, and also some measurements. So the specs for the board that were implemented at the time when we did the testing was 18 volts in, 12 volts out with 2 amps load current and a switching frequency of 200 kilohertz. We assumed an efficiency of 90%. Based on the calculations of the equations you've seen before, you'll see the duty cycle is 0.4, ripple factor is 40%. So ripple factor is associated with the ripple in the 2 inductors. And that ripple factor, the lower that value is, the tighter the ripple, the lower the ripple, which is a good thing from an efficiency and a losses point of view. But of course, it means that your inductance value becomes relatively large. And so is the size. So as you go up in that, the total opposite occurs. But 40% is a good default value as a starting point for your design. So based on all of this, we get 2 inductors, 2 single inductors of 45 microhenries based on the calculations. And the part actually we used was a VPD series. It's a 47 microhenry. It's a very popular series, and we've got quite a wide range of variants and sizes in this particular topology. And calculation milliamps of peak-to-peak ripple current in both inductors. So if we look on the side here, these are the actual measurements that were done on the prototype board. So we can see that the values that we have achieved here are very consistent with the calculations that were done. So on here, we see the voltage across inductor 1, inductor 2, and the 2 currents through L1 and L2, the input and the output inductors. So continuing on with the practical example on the previous slide, what I've decided to do here was just to expand on the input voltage range. So instead of it being a nominal or a constant 18 volts, I put 9 to 36. And we've kept everything else exactly the same as what we've seen before. And what I've done also is I've done some calculations to optimize the efficiency and the performance of your SEPIC. So in here, we've looked at 3 different voltages, starting with 9. Naturally, the nominal is 18, and the maximum or the top end is 36. Calculated the duty cycle, the average currents in both inductors, and we've come up with inductance values based on that input voltage, as you can see here, 21, 45, and 56. Now, the point here, or the point behind this exercise, is just to show you that naturally the value of inductance that you would be using has a big impact on that ripple current that you will be seeing in that inductor. So if we use the smallest calculated value, we end up with a relatively high current or ripple peak-to-peak current at the top end, at the 36 volts input. And we've also done the calculations for 45. That would be exactly the same as what we've achieved before, and at 56 microhenries. So with this side of things, you can do the calculation based on the middle value as a good halfway measure. If you go to the top value, naturally, maybe your size of your inductor might become bigger. The idea behind this as well is you do not need to do this we have got a tool called RedExpert that helps you optimize the selection of our inductors based on the SEPIC topology. I've included a link to RedExpert here with these specs built into the design tool for the SEPIC, and it shows you that it's more than capable of providing you with a wide range of inductors to use. The beauty about RedExpert, as well as you will see when you open the tool, is it provides you with the losses in the inductor, not just DC loss, but also AC losses as well, both core and copper losses. So you get a very good estimation of what you're going to see in terms of losses, as well as the temperature rise in the inductor. Now we'll move on to boundary conduction mode, or sometimes referred to as critical conduction mode. Now with the SEPIC, the definition of boundary is slightly different from the buck or the boost, where in those topologies, it's defined as when the current basically drops down to zero. In this case, because we have got two inductor currents, one on the input side, one on the output side, the boundary condition is based on those two currents summing up to the total ripple in the inductor. Or sometimes we can also refer to it as these two values that you can see on the curve here for those inductors. Basically, the minimums are equal and in opposite direction. One thing that we note here is the current doesn't actually drop to zero. It does go negative in the SEPIC converter. And when these two values here are equal and opposite direction, so sum up to zero, basically, that's when that's when boundary conduction mode, I should say, takes place. Now, this condition in the boost converter, it is IL2, which is the situation that you see on this curve that reverses, which makes sense because with IL2 is the smaller current in a boost topology, the current on the output, and vice versa. For the buck converter, or for the bucking function or mode, I should say, it is IL1 that reverses. We've also included the calculation for the load current at this boundary condition. So this is the minimum current, or the current, I should say, at which boundary condition occurs. So if we look at the previous example that we've looked at with 18 volts in, we have got an IOB of 0.47 amps, and the two equal values of the current would be around 75 milliamps. This here can be shown via simulation in LT-SPICE. I've also taken this boundary conduction mode one step further. In here, what I have done is use the boundary condition, IL1 plus IL2 equals delta IL, substituted for the values for each one of these parameters, and rearranged the equation with the purpose of identifying the boundary mode or the critical inductance. This is the inductance below which you will go into discontinuous conduction mode. So if we assume an efficiency of 100%. Naturally, the efficiency here is just to give us the input current referred back from the output power. And with that side of things, if we just assume 100%, just to simplify this equation, we see that this constant K, which is V out over F switching I out, if we consider that as a constant value, given a particular output voltage and a fixed switching frequency and a particular load current. Say you wanted to operate at 2 amps, but when your minimum load current is a half an amp, say. So you put in a half an amp here, and based on this equation, you will identify your critical conduction mode inductance value. What we see from here is that for a set load value, the worst case is at a minimum duty cycle. In other words, when Vin is max. So going back to the example we showed earlier, 9 to 36 volts, it would be the 36 volts end, which is the lower duty cycle, that will result in my calculation for my critical conduction mode inductance value. Now we'll move on to the other practical design consideration, which is using a coupled inductor or two single inductors. And these are the two topologies. As you can see, you can use just one coupled inductor here. Basically, both windings are on the same core. And here you've got the two single inductors, which is what we have been looking at so far. So with a coupled, naturally you reduce component count, you reduce board area, you reduce cost. So there are quite a few advantages from that side of things, but more technically, you need less inductance, as we will see on the next slide. So inductance value becomes smaller when you use a coupled inductor, and the magnetic coupling between the winding also allows us to do this ripple steering, which we will talk about in a little bit, and also having a leakage inductance between those two coupled windings also can be beneficial, which we will also look at on the next few slides. So from an inductance point of view, the inductance of a coupled inductor can be as much as half that of the inductance of each one of the two single inductors. So we talked about 47 microhenries. Here you can have half of that. And this is based on this equation here, L coupled over L single is 1 over 1 plus K. So what this relies on is this K, which is the coupling factor, which is what we can see here on the curve. So we've got coupling factor on the x-axis. Naturally, the tighter the coupling between the two windings, K approaches 1, and you end up with half the inductance. The curve actually doesn't show inductance, it shows it in the form of ripple. So the ripple of the coupled compared to the ripple of the uncoupled inductor. So this is one of the key advantages of coupled inductors. Now here we try to look at the impact of coupled versus single using some calculations and some simulations as well. You can see here we've got an LT SPICE simulation that we've run for a slightly different set of specs than what we've had before. So input and output duty cycle are all the same, but the output current is 4 amps, switching frequency is now 500 kilohertz, and the inductances are 10 microhenries each with a variable coupling factor K. So the idea behind varying the coupling factor is to show the uncoupled versus the coupled as you change that coupling. So basically what we've seen on the curve before. So with K equals 0 means no coupling at all, uncoupled inductors. So you've got two single inductors. Basically, delta I is 1.5. That's what you see here on L1, the input inductor. And of course, it is exactly the same for L2 from a ripple point of view. As you increase that coupling factor to get towards 0.9, you can see that the ripple pretty much halves. So there is the gray line here. You've got a lot less ripple for the coupled inductors. Naturally, this is the same inductance value, but we have got a coupled inductor in this case, which means that I'm getting a lot more filtering out of my inductor. The second advantage of using a coupled inductor is this concept of ripple steering. So how can we ripple steer? So if we introduce, first of all, an imbalance between the two windings, between the two inductors, so our turns ratio is no longer 1. So if you remember on all previous designs or slides, we have talked about an equal inductance value. In this case, we're intentionally using two separate inductance values, meaning the ripple is not going to be the same. Now, if we consider the previous example on the previous slide, and we look at a coupling factor of 0.9, but now a turns ratio between the two inductors of 0.95. Remember, this is a coupled inductor. So the symmetrical construction of the windings means that the leakage current is scaled by the turns ratio. So we have to consider now leakage between those two windings. So that's also another concept. We'll go into leakage in a bit more detail later. So if we consider L1, which is 10 microhenry as before, with a coupling factor of 0.9 and a turns ratio of 0.95, gives us a magnetizing inductance for L1, which is 9 microhenry. 10 times 0.9 gives us the 9 microhenries and a leakage of 1. And for the second inductor, the output side inductor, it will give us an 8.1 microhenry with a leakage of 0.9. Why 8.1? It's because of the turns ratio squared. So turns ratio naturally transfers voltages and currents, but it's turns squared that transfers inductance values. So it's actually 0.95 squared, which becomes 0.9. Multiplied by 9 gives you the 8.1 microhenries. And with 0.9 coupling factor, that gives us a 0.9 microhenry of leakage inductance. We will now use the LT-SPICE simulation to compare basically what we have seen a couple of slides ago, where n was equal to 1, the same number of turns, coupling factor was 0.9. We had a ripple current in both inductors of around 780 milliamps. But now, as we showed you on the previous slide, when we introduced this n equals 0.95, this turns ratio between the two windings, same coupling factor, we see that the ripple in L1 reduces quite substantially to 0.4 amps and increases in the second inductor L2 to 1.3 amps. So in this case, what we see is that the ripple current has been steered from one winding to the other, from L1 to L2 in this case. As a matter of fact, if you reduce an n to below 0.95, in this case actually 0.9, as you will see in that application note, the ripple current could be eliminated completely in L1. So why would we want to do this? We've got now a much bigger ripple in the other inductor. So this is mainly to improve the EMI performance. With L1 being the input current, if you've got very little ripple on that, it means that you have got a much cleaner conducted emissions profile. So the advantage depends on the application. So this is not something that can be applied across the board. It can be advantageous. Please look through the application note. There's a lot of detail on which applications this can be useful in. One other or a couple of other things that I'd like to mention here is do not oversteer, because you could end up with this current reversing and becoming negative, and that can become totally against any advantages that you might have achieved. And also note that both DC current levels are exactly the same, so that does not change. And now we come to the last practical aspect, which is this leakage effect of coupled inductors. Now we'll go back to a 1-to-1 turns ratio. And in this case, between those two windings, there will be a leakage inductance, which along with the AC capacitor, remember the capacitor between the input and the output stages, will result in what's called circulating currents. These are actually driven by the delta V AC across that capacitor, and it is superimposed on top of our triangular standard waveform that we expect to be running through the inductors. I've put in the equations for both the loop current and the magnetizing currents in each inductor. Now, if we end up with a coupled inductor with a very high coupling factor approaching 1.995, 0.998, I should say, and also a low capacitance value, low CAC value, this loop circulating current dominates the waveform shape, and it is a third order polynomial shape. You can actually see what it looks like here in the measurement that was done based on a K of 0.995 and a CAC of 1.5 micros. So this is a very tightly coupled inductor. You end up with a very high peak-to-peak ripple in this situation. This inductor ripple is no longer triangular anymore. The ripple is considerably higher in value, as you can see, and that results in considerably higher losses and temperature rise in the inductor. One other thing, this increased ripple is not contributing to the energy transfer from the input stage to the output stage. It's basically a waste. So what can we do about this? We can increase the AC capacitance value. That's not necessarily sometimes the best option on a cost and a size point of view, but we can also increase the leakage inductance. So we're trying to offset that loop current to minimize it basically by doing either one. And this is a good option, the increase in the leakage inductance, because it is something that we can already have in our inductor. So just design a coupled inductor basically with a lower coupling factor. So and again, for L1 equals L2, the same status that we have talked about earlier. CAC, the capacitance can be calculated based on this equation as a minimum capacitance. So that's just to show you what the minimum capacitance needed based on an L value. And using a high leakage coupled inductor, in this case K equals 0.7, so this is substantially lower than the one that we've seen on the previous slide, we reduce the loop current quite substantially. When we haven't done anything to our CAC, we kept that at 1.5 microfarads. So that stayed the same. Now we have got our good old triangular waveform, which we would expect in an inductor, improved efficiency, 0.3 amps peak to peak, not 3.2 amps peak to peak. So that's one key practical aspect of selecting a coupled inductor for a SEPIC converter. And also just to show you the thermal performance comparison between a low leakage and a high leakage coupled inductor. So naturally the high leakage is the better one, as we have alluded to earlier. So you can see here, this is not the same prototype board, it's a different one actually, but it shows you the difference in temperature rise in the component as a result of the increased losses now because of that circulating or loop current. And so how can we achieve or increase the leakage? We show you here some of the winding techniques that we use in our coupled inductors. So if you have them stacked, as you can see here, or sectional wound, you end up with a considerably higher leakage inductance. You have got the one layer design, so that's an intermediate leakage. If you've got bifilar wound type inductors, it's low leakage, and the sandwich is the very low leakage type inductance construction. So with these different construction values, we can achieve more control over our coupling factor basically and leakage. And just to show you an example of one of our product series, the VDD, it comes in two variants, the straight and the crossed, as you can see here. And with the crossed, you get higher leakage inductance. So this is a very popular series with a very wide range of inductances and sizes available in our product portfolio. And talking of product portfolio, I'm just showing you a few parts here. Now, this is not everything. So just to give you an idea of the wide variation of different technologies that we have in terms of the coupled inductors. So we have got the molded type, this MCRI. So this is a composite iron powder with fairly high saturation and high coupling coefficient. And we've got the air-gapped type coupled inductors, the multi-turn coupled inductor, the DPCHV and TDCHV. Both the HVs mean they're higher voltage, so they've got higher level of isolation between the two windings, should that be required. Naturally, SEPIC is not the only application for these coupled inductors. So I'll finish off with one last thing regarding coupled inductors in terms of other things to consider, since we're talking about construction and different types. Rated and saturation currents as defined in the datasheet is very important. So I would suggest looking at how that actually has been measured. Has this been measured with the windings in series or in parallel or as a single winding? So worst case scenario would be IR in parallel and ISAT in parallel or single. So that'll give you the maximum rated current and the maximum saturation current in the inductor. Also consider soft and hard saturation from a temperature effect point of view. So there we've got a wide range of different topics that we cover on the impact of temperature on the saturation characteristic. And finally, of course, the percolation effect, where we also have a full application note to explain the impact on molded type inductors and voltage rating. On the last few slides, I've actually used models for our inductors, the VDD series and the MCRI series, which I've mentioned on the earlier slides. I'm again showing you the different coupling factors. I've simulated this in LT-SPICE using the models for those two parts. And this is, again, the idea behind this is to show you can actually use those models because they accurately predict the behavior of the component with its coupling factor based on the accurate models that we have got for these parts in LT-SPICE. And that shows you, again, the impact that a low leakage inductance has with a much higher ripple third order polynomial, as we have mentioned on the previous slide. And 3 more simulation results as well, again using LT-SPICE, and that was based on actually controlling the coupling factor with 3 different types of scenarios. Option 1 is what we have been proposing, which is use a low K type high leakage inductance inductor. And in here you see the big difference between the triangular waveform, be it on the input or the output inductors, compared to the much bigger, higher ripple for the lot lower leakage type inductance. So this is the operating conditions based on a constant CAC, constant switching frequency, and it's only the leakage that is changing, just to show you the impact that this has. And the second option, of course, is to use a bigger AC coupling capacitor. Here we have fixed the leakage inductance, and we are looking now at a difference in CAC from 2.2 microfarads to 10 microfarads. And again, you can see the advantage of having a bigger coupling capacitor. So it's the same concept as increasing the leakage inductance, but the leakage inductance is a freebie. It's part of the actual coupled inductor. And option 3, last but not least, is increasing the switching frequency, which we've increased from 450K to 1.2 megs. That's not necessarily always the best solution, because we know increasing switching frequency also results in higher switching losses. So, but it is an option, so I thought to also include that. I hope you found this useful. Thank you very much for your time, and I'm happy to receive your questions.
Okay. Yeah, thank you, Mohamed, for your interesting presentation. Now we'll come to your questions. Before we start with the live Q&A, I will start a handout from the presentation from Mohamed, and then everyone can download it. So yeah, okay. Yeah, now everyone can download it on the right side on the black button. Okay, Mohamed, are you ready for the questions?
As ready as I can be, yes. Good morning, everyone. Hope you're having a good day.
Okay, cool. Then we start directly with the first question. Does the Red Expert tool calculate the SEPIC for single or coupled inductors?
Okay, yeah, that's a good question. Yeah, of course, the SEPIC tool does calculate it for both. So you have got the option in the design tool, which is on the side of Red Expert, on the side of the coupled inductor selection tool, to select whether you wanted to use a single inductor or 2 single inductors or 1 coupled inductor. So you have got both options, and it will do the calculation on both bases. So the link that I have included in the actual slides does give you the option, and you can just flick across that switch to use a single or a coupled inductor, and it'll show you equally the losses and calculate the ripple, as well as the temperature rise, as I mentioned, in that component. So it makes life a lot easier from you having to do the calculations yourself. But I mean, at the end of the day, between starting off as a good starting point with the SEPIC tool in Red Expert, I would say the next step would be to do some level of simulation, and of course, finally verifying the whole thing onto an actual prototype, like Ilyatar has done when he did the application Node 135.
Okay, thank you. Very cool. Thank you for the answer. Then, next question. Okay. Can you use coupled inductors for a 2-phase boost converter?
Yeah, I believe yes, you can use them for a 2-phase boost converter. I'm not 100% certain. I mean, naturally, the same advantages as what we have mentioned before with the reduction of size and cost, and that will always be an advantage. I'll tell you one thing else that I have used coupled inductors for. It was the output of a forward converter, where we had multiple outputs, and we had, of course, a coupled inductor with the same turns ratio between the various different outputs, 5, 15 at the time, on that output as well. That doesn't just save you size and cost, but also improves the inductance. From an inductance point of view, you get a better performance, as we have mentioned here, with the coupling factor making a big difference in terms of the amount of inductance that you would require. You still have to watch out for circulating currents, though, the loop currents that we've mentioned before.
Okay. Then, next question. We had a lot of questions in the chat, so very cool to see. So yeah, continue with the next question. Do I have to make custom transformers to make this asymmetry in radio, or do you have standard ones?
That's a very good question. Well, custom coupled inductors, I guess, and it is one of the things that I have alluded to in the slides, is with regards specifically to ripple steering. And I think when you're talking about an asymmetry in the turns ratio here, we're talking about the ripple steering side of things. So with ripple steering, I think it's something that is application based, and I mentioned this. So certain applications would require you, or would be more beneficial for you, to have more control over that turns ratio, because we could see from what I have put in the slides, and what's also been very well documented and written in the application note, that you oversteer, you could end up being in trouble. It's like you're steering your car, and if you oversteer, you end up going back on yourself. You do not want to oversteer. So my point here is control over that turns ratio, that N, becomes quite important and critical. So if you wanted to do that, a custom inductor would be the way to go. And we can do these with Worth as well. But again, this is very much reliant on applications. So things like power factor correction, things like more higher power type DC-DCs using the SEPIC topology, this is where I would say maybe it's worthwhile considering more the custom solution from a ripple steering point of view. Why? Ripple steering, the concept is primarily there to reduce the ripple on the input side, so that you do not have to use a lot of EMI filtering. When you have got high powers, high currents, high voltages, designing an input EMI filter becomes expensive and costly, and so on and so forth. Not that you can't do it, not that we don't have parts to do it, we can, but it's always a balancing act. So for that type of application, ripple steering can be useful, and maybe more of a custom solution may be the way to go. For the majority and the standard mid to small levels of power, it makes more sense to use a standard off-the-shelf type inductor. And we do have a certain level of ripple steering within our parts as well. I mentioned the VDD series. So that would also give you a little bit of that.
Okay, thanks. Then, next question. The VE DPC SMT dual power choke family is not boarded to be used in SEPICs converters. Can you comment on the reason?
The VDPC HV. The HV is usually the higher voltage side of things. So with that, I would expect the DPC to maybe more be applicable to things like the fly buck, for example, which I know is being used in that type of application. But I'm not sure as to why it is not to be used in a SEPIC converter. Nothing comes off the top of my head. It may be more advantageous to use it elsewhere, but I mean, nothing comes to the top of my head as to why that is the case. So I will have to get back to you on this one. I'm not sure as to why that is the case. So if you leave us your details, I think it's Henning, then we can get back to you on this answer to this question.
Okay. Okay, then I would say one last question. Do you have an application notes for planar inductor designs one can use for designing customer inductors?
No, I'm afraid not that I'm aware of. There may be something that is in the pipeline that we're looking into, but I am not aware of any type of application note for planar type designs. I have worked on planar type in design, design inductors, transformers, of course, more particularly, I would say. Even integrated magnetics in the past, but I'm afraid no, we do not, as a Worth Electronics. I am not aware of any of these. But again, if you can leave us your details, then what we can do is we can come back to you on anything that comes up or is coming up in the pipeline for these application notes.
Thank you. Then I see one more question in the chat. Very cool. Then, why the increased frequency 1.2 megahertz in LT-SPI simulation also shifted the average value of inductor?
No, it wouldn't change the average value. The average value would stay the same. It would be two different values for the input and the output inductors, naturally, from an average point of view, depending on the load current and your input voltage as to what you end up with, or your bucking or boosting, in other words, as to what your averages would be. But the increase in switching frequency would only affect the variation in averages based on the losses that you may get in the system. So if you're increased losses as a result of the lower efficiency at higher switching frequency, yeah, you may end up, of course, with a higher level of average current on the input side, because your efficiencies drop now a bit lower than before. So that can be the main effect. And if you look again at things like the leakage effect that we talked about at the end of the presentation, where we were looking at the bigger ripple inductor that you end up with as a result of that third order polynomial, that is a substantial amount of loss that you are ending up with. So that will affect naturally how much input current you'd require, because of your efficiency now is dropped down quite substantially as a result of the increased losses. So this is where sometimes things like that higher ripple, or naturally switching frequency, all of these various different effects can make a difference to your average if we're not looking at ideal conditions, of course.
Okay, thank you, Mohamed. Then I think we are finished with the session today. Thank you for your time, Mohamed. Thank you for your presentation and for all the answers. Yeah, cool to have you here.
Thank you very much. It's my pleasure. Enjoy the rest of your week, ladies and gents, and look forward to seeing you next year.
Yeah. Now I share the link. So we have a lot of other sessions during the week at the Digital WE Days. So we just now don't forget your chance to participate in our sessions. So for the Europees, have a great lunch. Thank you for joining, and for all the others, have a nice day and bye-bye.